Gaussian process, we started with the application of Wi-Fi-slam. And you know that Wi-Fi-slam is about what? It's about a fingerprint, right? How could we build up a so-called fingerprint of a location or some states, right? Fingerprint is nothing else than what? And a feature list, right? It's just to get a bunch of feature list, right? For a given location, and then you will have a vector. This vector maybe it's just the RSSI of all the access points, right? It's just RSSI values. Okay, that's the AP first one, AP second one, the RSSI values, right? Typically, this is the case. And also, you can imagine if you don't do a Wi-Fi-slam, but other localization or anything related to the states, the localization states. For example, use a magnetic feature or some visual feature. All these can serve as a fingerprint or a place, right? Maybe you can build a descriptor for the topology of the local environment. Okay, that's also a fingerprint. It's nothing else than a list of features. So the key problem is you will collect these features only in a quite sparse way. Right? You can only collect these features sparsely. We give an example that if you want to do the Wi-Fi-slam, you put 5 access points or Wi-Fi routers, right, in the environment. Then every location, you will receive a feature list, right? This feature list, for example, this is the RSSI value for log 1, log 2, up to location 5, location 4, location 0 to 4, right? 3 and 4. So this serves as a fingerprint. What is fingerprint? Fingerprint means it's unique, right? If you see this fingerprint, you can use that to infer back, right? This is called diagnostic reasoning, right? I have this observation, oh, I want to know about the location X, so I want to compute this post area, right? This post area. How can I get this post area using Bayesian, right? Use a Bayesian algorithm, and you have the Px given O is a PO given X times Px over PO, right? Okay, this is clear. And for Gaussian process, the problem is how can we compute a likelihood, right? How can we compute this likelihood? For example, the P of O given X, right? Given the location, what can be the possible fingerprint, right? What can be a possible fingerprint? And we know that this is a regression problem, right? This is a regression problem, and well, we collect all the median values for one of the router. You can collect for all the 5 different routers, and then you can do the regression, right? The result of the regression is you get the mean field for the one of the router, or of course you get the mean field of all the 5 routers, right? If you collect all the data sparsely, and then at every location, you get this PO given X, right? You get this PO given X. How would that be possible? How would that be possible? Because it's the result of regression, and that's the result of a Gaussian process, right? The result of a Gaussian process. You can try to use a linear regression, but the problem with linear regression is we mentioned already. We discussed already the uncertainty, right? Linear regression cannot provide the property like if you have more points in the neighborhood, and then you have lower uncertainty. So by nature, that's not the case, okay? Because you grant some uncertainty to the data distribution already, right? That's why you use the quadratic form, right? The mean square error to minimize the overall error, so that you get this optimization as a result of the regression. Yeah. So that's important to have the mean, and also important to have the variance. That means how much uncertainty how much uncertainty you can have. So as a result, we learned that the Gaussian process basically is a distribution over functions, right? What is important is the kernel, defined as a kernel. The response of the kernel indicates the similarity, right? Indicates the similarity. If the two x are close, then the response of the x, y, or x, they should be similar. Right? That shows the similarity. The greater value you have for the specific kernel for x and x prime, greater k means higher similarity. And you can get samples, right? Get sampled from this kernel definition. Okay. In other words, it's basically the correlation, right? It's basically the correlation. And then we give a series of examples. In these examples, we try to use the given data, the existing dimensions, to cut a slice, right? Get a slice of a Gaussian distribution, and use that distribution to further do the reasoning. Okay, that's where we stopped. That's where we stopped last week. One quick question. Recap one, a kernel in this case is symmetric A, B, C, and D. Which one? A kernel. Like this is these are samples from a Gaussian kernel, right? A kernel is what? A, B, C, D. Which one? Which ones? It's an inner product. A kernel is also what? It's also symmetric and also semi-definite positive, right? Okay, ABC, ABC. Okay. Back to the origin of the why we discuss this question. So we discuss this question because we want to easily infer the likelihood. Right. Given the location, what will be the fingerprint of the set of Wi-Fi? You ask for lecture questions. Let me figure it out. Okay, that's the things we want to infer. Right? Given the location, what can be a typical fingerprint? Right? What can be a fingerprint? Or what's the likelihood? And so far, the regression expressed with respect to the basis function, right? With respect to the basis function. Sorry. Like in a typical regression, when you provide the group of xt's, you compute the phi of x, the design matrix, and then take the pseudo inverse of this phi x times t. That give you what? Give you the w, right? Give you this w. And then you will use what? You will take the w in a product with the phi x to define the new y, right? That's the previous regression fundamentals. So the focus is on the computation of weighting vector w, no, on the weight vector w. If you want to do regularization, you just slightly change the, let's jump over, I don't know what. You just add, use a modified pseudo inverse, right? Use a modified pseudo inverse. So with a Gaussian prior on the W, if you have some Gaussian prior on the W, then this learned Yx is what? This is an example of a Gaussian process. Okay, this is just the example of a Gaussian process if the W has a Gaussian prior. Right? The W has a Gaussian prior. if you still recall, or the incremental regression, every time you add 1 point, every time you add 1 point, and you get samples from that point, and finally you can incrementally learn a function. In that example, we have some priors, right? Some priors, which is Gaussian on the W, right? Because we want to minimize the size of the W, also help the regularization. So that case is a special case of a Gaussian process, right? A special case of a Gaussian process. But now what do we want to solve? We want to come back to the probabilistic formulation. For example, this one, how can you learn this likelihood? How can you learn this likelihood? We want to get rid of the W and the phi of X. Okay, get rid of that. More intuitively, we want to estimate the T for a new point X directly. Okay, we want to estimate the T from the new X directly. What's the difference between this method, like a Gaussian process, and regression? So this is a key difference, right? So far, the regression is you want to learn a function y, so that if I give you a new x star, you can compute what will be the new y star, and use that y star to approximate the inherent function value, right? That's what you had so far for regression. But for Gaussian process, we don't want to learn this function. You just give the pairs, of data, of these data points, and you ask the question, if I want to compute what will be the corresponding fx given this x, what will be fx? I don't want to first compute a y function. I don't have this function. Instead, you want to directly infer from x to fx, right? So this is the scalar, right? This is a value of x, or some features you learned, right? You want to do that directly instead of some explicit functions in the form of y equals to inner product of w and px, and w and phi x, right? Okay. That's some advantages and also some challenges. But we are encountering some noisy observation, right? Noisy observation. This is quite normal, right? No matter for the Wi-Fi signal or any magnetic observation, or even the LiDAR sensor reading or camera features, they will be noisy. They'll be noisy. So how can we model this noise, right? We model the noise by to the regression. You have some core function y plus some noise, right? Plus some noise, and we consider the yn is the nth component of y, right? It's like the previously you have a 25-dimensional Gaussian process. Sorry, 25-dimensional Gaussian process. It's just considered as the nth component of the y. And everywhere you have this Gaussian noise, right? Everywhere you have this Gaussian noise. Like if you know about the y, and then the distribution of t is a Gaussian, and overall the multivariant t is also a multivariant Gaussian with a mean at y. And you have this uncertainty. This uncertainty initially you can set to 1 over some beta value. Then what is the co-function py? And you can set the mean of this y to be 0. Or you can set the mean of the y to be 0. Why that? Because if you don't do that, then the covariance of y will be y minus the mean times y minus the mean transpose, right? So it's not that direct, but you can shift all the y values by the mean, and then you have 0 mean, right? So this operation doesn't affect the nature of your data, right? It's just move all the points up and down together. Okay, this page is important, right? This page is important. We want to compute the probability distribution of the predicted t. Okay, what will be the distribution of the real data t? And we know this distribution is nothing else than a joint distribution of t and y, but marginalize out this y. Right. Inside is the joint distribution of t and y, right? Marginalize over y, you get pt. Then we can expand each of these following the previous page. And finally, you will have t should also follow a 0 mean if you set the mean of y to be 0, and with the covariance matrix C. The C is this guy. Right, C is this guy. What's that? That's C. What's the covariance? This covariance basically follows the previous kernel, the kernel you picked, following that kernel, with additional variance introduced by this new point. Right, introduced by this new point. That means if you want to do a prediction on some like if you want to do the prediction of the O, but you know the previous distribution of all the O's, right? I want to predict from X star what will be the O star. How do you do that? I just build a covariance matrix over all my previous, this is the K, right? I build a covariance matrix over the previous observed data, and then adding one additional column and rows. Okay? One additional column and row. Well, in this case, the complexity, you see the overall matrix, if you have n data points, and then the overall covariance matrix is n by n, right? N by n. You see you have n data points, x1, x2, x3, up to xn. This is also xn. So finally, you have n by n matrix. That's the covariance matrix complexity. Okay, we quickly wrap up why we're talking about this. Okay, and this definition is also interesting and important. We use the Gaussian process because of what? Sometimes if the problem is more or less like a fingerprint related problem, for example, the Wifi-slam, right? Every X will be associated with the O, and you can do the experiment in a quite limited way because you cannot fully cover everywhere, right? So you have these scattered observations. Our goal is to simply predict what will be, given the location X, like this position X, what will be the fingerprint, right? What's the distribution of this fingerprint O? In the previous regression problem, how do you solve that? You want to learn a function Y, and explicitly learn a function Y, so that given a new X, you can compute, right? What will be the Y value? And that Y value follows also a kind of distribution, right? So in Gaussian process, I want to get rid of this intermediate process, right? I don't want to compute the explicit function Y. Instead, well, you tell me how these feature distributed, I can directly compute for this given X, what will be the distribution of the O, right? The P of the O, given the location of this X. Okay, based on what? Based on all the previous observations, right? Based on all the previous Like this is O1, this is O2, O3, and all these observations. This data can support all these observed data. They will support my inference of this likelihood. All right. Another way you can understand it as a mapping, right? It's a mapping. For a given location X, I can map that to some set of points in the space of O, in the fingerprint space. Now, with a new X star, how can I do the mapping so that I get the O star? I just check the nearest neighbors, right? Check the neighborhood. Check the neighborhood in the O, and then I can use the neighborhoods. Consider the neighborhood in X space should also be the neighborhood in the O space, so that I don't need to learn this explicit function Y. I don't learn this explicit function Y of X. I directly use the existing O, or this the learning data O, the training data O, to directly infer this O star. Okay, directly infer this O star. How could we describe this bunch of wording in an equation? That's exactly the equation we just discussed. Well, it's too long. That's exactly this equation, right? Because if there is a latent variable Y, with this Y, you can use this Y to easily predict the T, right? You can use this Y, and well, the distribution over T over Y is simply a normal distribution at the mean Y, mean as Y, and with some variance Y over 1 over the beta, right? Right? If there is such a function of Y. But we don't like such a kind of function, and sometimes because there's no way to show that explicitly, right? Like how do you write a function, map a location XY to a 100-dimensional RSSI value of the Wi-Fi signal, right? This kind of function is sometimes impossible, right? Impossible. But I can directly infer the T. Why that? Because I can marginalize out this Y from this joint distribution, and this final term shows that, well, I have this distribution already, right? The distribution is also a Gaussian. If you have a zero mean on the Y, then this distribution of T is also a Gaussian. Now, what's the Gaussian? It's defined by the mean and the variance, right? The covariance. And the covariance matrix is with a dimension n by n. Okay, n is the number of total data you have. So whenever you add a new point, you are just adding a new column and a new row, right? New row and a column. Okay, then you have this covariance. Now how do I compute the value of T? You just get a slice, right? Get a slice over this covariance matrix. As for the kernel, I have this kernel K, right? This C is also symmetric and positive definite because the K value in between, so every pairs of the combinations of K, you have this the response of the kernel function, right? So it's a kernel function. So C is nothing else than the kernel function of K11 up to KNN. Here is a K1N, KN1, right? And you also have T K12 or something, right? So this is a C. You can pick the kernel function K, right? Pick the kernel function K. It can be a Gaussian, can be anything else. So in this case, K is preferred to be a Gaussian. If it's just symmetric and a positive semi-definite, then this is already a kernel, right? This is already a kernel. We prefer a Gaussian, but not necessarily a Gaussian. And the choice of this K depends on application. You can build that from the feature functions, like build that from the phi. Then how do you define the K matrix? K is just a phi T, right? K is just phi T. Or you define this K matrix directly, as long as this K is symmetric and positive definite. In general, for more similar points in X, the response of the Y space, they are more correlated, right? and the value of k, xn, xm shows what? Shows this, indicates this similarity, right? This is just the similarity. The similarity of y of xn and y of xm, right? It just indicates the similarity. Good. That's how the kernel, put in use. For example, you can define this phi matrix as a 1x, right? 1x, that means it's also a polynomial. Quite similar to what you learned in the linear regression. And the k is this one, right? 1 over phi t phi, inner product of the phi's. And the common kernel for the Gaussian process regression can also be defined in a general way, right? This is the general definition. So you can use maybe 1, 2, 3, 4 parameters to define the properties of this kernel. That means you can directly define a kernel as well. So give you an example how the kernel, in this case, should look like, right? This is a generic form. And then you can give assign the values for phi 0, phi 1, theta 0, theta 1, theta 2, and theta 3. Okay? Then you can assign these values. And then you can get samples, right? Get samples from every kernel. How do you get the sample? You watch the YouTube link, right? We introduced in one of the slides. Then you get the samples. Okay? From this definition, you could easily see that the phi 0, theta 0, sorry, theta 0 is the relevance of this proximity. And theta 1 is the scalar, right? If you choose a larger theta 1, that means you get a smaller neighborhood under consideration, right? Theta 2 is the noise. Theta 3 is the linear parameter form, right? If you have theta 3 in a greater value, that means you want to grant more linearity. Like this, right? You see, first you check the theta 3. All of these cases, they are of 0 for theta 3. So that's why you get all the lines more smooth, right? It's horizontally distributed, quite smooth horizontally. But if you have the theta 3 as a 5, then you get my dynamics, right? Dynamics like the ratio approximations or the proportions of the functions. And about theta 2, that in this case, the theta 2 has a much greater value, and then you get more noise, right? Get more noise. And theta 1 defines the neighborhood, right? A greater theta 1 means you consider a smaller neighborhood, right? So you get only the similarity in a smaller neighborhood if you have greater theta 1, like this one. Okay, and if you have a very small theta 1, that means all the values, all the responses should be similar. So the dynamics, the function will be more smooth, right? The dynamics is reduced. So that's the definition of some kernel, right? You can define a function, a kernel function, by choosing the theta 0 to theta 3. Then what? Then you construct this C matrix. Construct this C matrix. Then you can do what? You can directly predict, by inputting all the x, you can directly predict what will be the distribution of the new y. Okay, here's some example. As a prior, you don't have any idea. As a prior, you don't have any idea before the learning of the function. And after some time, you will learn a distribution which is more served as a posterior, right? Like you're getting a slice of this multivariate Gaussian. So for the prediction, what is the prediction? Given the pairs and XOs, I want to know that if you're asking for a new X n plus 1, what will be the distribution of the PO n plus 1 given new X1, right? This is a prediction. This is a prediction. So you have a new input vector X n plus 1, and you have the existing t values. You want to predict what will be the t n plus 1, right? Or predict what will be the t n plus 1. Okay, how do you do that? It's a joint distribution. You see this is a capital T, right? This is a capital T because you have everything inside. The joint distribution of the Tn plus Tn plus 1 over the distribution over the Ptn. The Ptn from the previous slide, it's zero mean is the variance of Cn. And Ptn plus 1, zero mean, and Cn plus 1. What's Cn plus 1? It's just adding one row and one column, right, to this covariance matrix C. Right, adding this new column and rows. So if you want to predict directly the value from the existing data set Tn, then this is a Gaussian. Right, this is a Gaussian. Similar to the discussion of the previous week, right? It's basically you take out all the existing values. By looking at this covariance matrix, you make a cut, right? Cutting the middle. Like if you cut a two-dimensional Gaussian, you get a one-dimensional Gaussian. You can use that distribution to deal with the prediction of the mean, right? So the prediction of the mean. Why this is the case? There's a quick discussion last week, right? Quick discussion last week. And this one is also a linear combination. This is important, right? This one, if you don't care about this one, and you should know that this is a linear combination over all the kernel functions, right? Over the kernel values. And what are these linear combination coefficients? This coefficient is the C inverse times T. C inverse times T. Does that remind you something? Because, well, it's similar to what? Like in your linear regression, you have the format of Wt times phi, right? And T times phi x. So what's the phi x? The phi x is the feature vector, right? It's a feature vector. So how do you get the W? The W is the pseudo inverse of phi, the phi times T, right? You see, these two guys, they have the similar format, right? It's an inverse of the C, but in the previous linear regression, we know this is a pseudo inverse of design matrix phi. What's a design matrix phi? And then it can be expanded as also the correlation, right? Expanded as a correlation. Okay, there are difference, but you can have this intuition, right? This is intuition that the mean is also a linear combination of the feature vectors, right? Linear combination of the feature vectors. Okay, what about variance? Variance is just a C n plus 1, right? Adding one row and a column. So once you have this distribution, you can easily get a sample from this distribution, and then you can do the prediction of the t value of the of n plus 1 directly. The complexity is you should know that this is the mean. This is a linear combination of the kernel response, and this is the variance, right? And that leads to inversion of Cn, and the Cn is an n by n matrix. So the overall complexity is O. Well, you can use Cholesky decomposition to help with the decomposition, to help with the inversion. But the overall complexity is O n cubic. And the standard regression, you need to do the compute the pseudo inverse of the phi. The dimension of the phi is n, right? Is n by n. Right? That's the design matrix, right? So when you compute the pseudo inverse, you should compute the phi t phi inverse times phi t, right? This inversion, this is n by n, right? Because it's a phi t times phi, right? So that's the complexity. The standard regression, the complexity is in O m cubic. The regression with the Gaussian process is n cubic. N is the number of data points. Right? M is the system complexity. So that means it's useful for feature space of higher dimension than the number of data points. Right? If you have a higher dimension and you don't have so many data points, then probably you can think of using a Gaussian process. If it's very cheap for you to get the data, and you can use more data for the training, and then you can also use the standard regression. Okay, this is the complexity. As a summary, the regression with the Gaussian process, it's in the function viewpoint instead of parameters, right? We directly learn the function instead of the linear combination coefficient, right? You don't have parameter, but you directly have a function view. Secondly, a Gaussian process is a probability distribution over functions, and data points constrain the distribution. And definition, you have a kernel, definition of a kernel, and use that kernel to describe the covariance. You have implicit feature space because you directly have the C. C is the covariance matrix, and you should know that the C also you can call that the K matrix is the phi phi t, right? So you have an implicit feature space, and you directly define this K, and you don't know about this phi, right? It's not explicit. So it's an implicit feature space in K, and the complexity is in terms of data points, right? So it's O n cubic. So this is a summary of a regression using a Gaussian process. Okay. So question 1, with the help of this covariance matrix, the prediction of the value is which one? A, by extracting a slice of the joint distribution, is A correct? The prediction of a value is extracting a slice of a joint distribution. The prediction of a value, like I want to know what is the t of n plus 1 given the t of n. T is a vector, right? This is true or not? This is what? This is the truth, right? This is true. Like the multivariant Gaussian, right? I can easily predict a new value from the given covariance matrix and cut a slice, right? By cutting a slice, and you get the distribution of the predicted t. This is the truth, and it is posterior It is the posterior. Because you derive n plus 1 from t, right? So you do have a, if you say this a posterior, that means you have a prior, right? You have a prior, you have a likelihood, so that you get a posterior. So it's not necessarily a posterior, right? You can directly infer the similarity of the data. How do you measure the similarity? The similarity is what? The similarity is the amplitudes of the entries in the covariance matrix, right? And C, it can be a prior for the state estimation. This is true, right? You can use that as a prior. Use it as a prior. It's a directly readable value. Is that a value? It's not a value, right? It's not a value. It's a distribution. Right? This is a distribution. We cut a two-dimensional Gaussian. We get a one-dimensional Gaussian. So finally, this P is a distribution, right? Question 2. For newly given data, you need to update the covariance matrix. So A totally updated, B add a column, C add a row, and D add a column and row. Which one? D, right? D. Well, more answers from audience. Good. D. Question 3. Compare with a linear regression. Right? Compare with a linear regression. Gaussian process A has a much lower computationally complexity. Is this true? False, right? What's the complexity? This is O n cubic for Gaussian process, right? Linear regression is O m cubic, right? Depends on the dimensionality of the problem. And B, A is true when the number of trained data is large, or C is true when the model to be predicted is complex. Which one? B or C? C, right? C. And D can also be understood in terms of linear regression when the coefficient W and the output is jointly a multivariate Gaussian. So Gaussian process is what? Is a linear regression. If it's a linear regression, where the coefficient W and the output is jointly a multivariate Gaussian. Is this true? No, right? So actually, there are several conceptual questions, quite silly, right? So the coefficient W and the output, basically they're from different space, right? Firstly, these two space, you don't have a joint. You can define joint distribution, but this distribution definitely is not a Gaussian, right? Because you try to take all the variant, the features, right? The output is the linear combinations of the by W times the feature, right? Times the feature. So some values from the feature. And you said that it said that the W and this guy, they are jointly multivariate Gaussian. So this is not true, right? You can say that you can grant some prior on the W, and that prior is a Gaussian, and then that's a special case of the Gaussian process. And also that's a linear regression, right? So D is not so relevant. Okay. Question 4: if you're asked to design a Wi-Fi-SLAM, that means using the Wi-Fi signal you observe to localize yourself, right? Also, you create a map of the Wi-Fi signal distribution. So what may be the minimum sets required? What will be the minimum input? What are the data needed? Right? What are the data sets needed to create the Wi-Fi SLAM? So A, the sensor to measure the RSSI signal from the test points. This should be true, right? Otherwise, there is no sensor. And B, ground truth of location where you took this measurement. Do you need that? this as a typical Gaussian process, this should be true, right? This is true. And see a process to predict the RSSI at a new location. If you want to do a Wifi-slam, do you need a process to predict the RSSI at a new location? No. Right, no. Because you directly build what? A data model, right? You don't need the process to predict the new RSSI. You can directly construct the distribution of the RSSI at a new location. So basically, the process means what? You need a function, right? You need a function. So you don't need such a function. A process to predict the motion. If you want to build only the Wi-Fi signal map, you don't need the prediction of the motion, right? But if you want to have a localization, if you have such a prior, this can have this function, it can serve as a prior, right? It's not necessarily need, right? It's not in the minimum set requirement. Okay. Some extension from the answer of B. We know we want to know the location X, and want to know some observation O, or you can call it know the X and the T. Right? You want to know X and T as your training data, right? As the training data. This is understandable, right? If you give that's where you took the measure and what's the Wi-Fi signal. This is very nice. But I also want to remind you that there are some redundancy between the XT as well, right? Why do I say that? Because we will mention that if you have the kernel, let's say for two locations, X and X prime, if you have a higher response in K, that means you have a similarity. We can denote that as a T of X or T of X prime, right? It doesn't hurt to denote that. The similarity also shows the K also shows the similarity of these two values. So there must be some redundancy, right? There will be some redundancy. How do you understand this redundancy? If I have two locations, these two locations have similar T, right? Look at the problem from the other direction, right? If I have two observations, one observation read all the access points feature, a second observation do a similar thing, and I check the similarity of these two measurements, and they are quite similar. That means what? That means the locations X and X prime, they will be quite close, right? At least as a prior, right? As a reasonable deduction, right? If I have a similar T, that means I have a similar X. Actually, that sometimes this organization, the self-organized structure, by only observing the T, will give you some structural information of this X as well, right? Think about that. If you have the similar X, that means you get a similar T. What does that mean? That means the information contained in the X and information contained in T, you have some redundancy, right? You have some redundancy. In terms of, I don't know, the information, right? Information theory. The information contained in X minus the information contained in X by knowing the distribution of T. This is what? This is called the mutual information between the X and T. Okay? In many cases, we can maximize this mutual information so that you get the best description of the best description of the mapping, right, from X to T, right? So it's an optimization problem. Also, that's what it's a regression problem. Also, this is the optimization problem of this mutual information I. Right? Also, this is the optimization of this mutant information I. So because the information containing X has some overlap with the information containing T. That overlap is called the mutant information, right? In X and some in T. In the middle, you have the I of xt, right? Good. From this, you can tell what? I do not need to have the full structure of the X because I can explore the similarity in T to infer what will be the structural possibility of the X, right? If you have a 1,000 readings, right? This 1,000 reading or with different T values, by exploring the inter similarity, maybe some dimensions in the first measure is quite similar to the sum of dimensions in the measurement of maybe number 10. That means location-wise, there either will be some symmetrical information or something else. The location number 1, the location number 10, they have some relationship, right? They have some relationship. And with this relationship all exploited, and the structure of the X can also be possibly reviewed, right? It's also possibly reviewed. It seems like a very fancy theory, but actually there are also some theoretical work in this direction, right? Some theoretical work in this direction. If you do the linear regression or the regression from X, you want to learn a function Y. That's why you're provided with pairs of XTs, right? Many of the training data. And finally, you learn a function or something, right? So with the support of the theory I just mentioned, I don't need the X. You just give me a bunch of T. And as long as I know there are some mutant information between the X and T, only by knowing the distribution of T, I can use the T to infer what will be the dimension, what's the structure of the X should look like, especially if the T has a higher dimension than X, right? Especially when the T has a higher dimension than X. So if X is the location of a robot, and Y is, for example, the sensor reading, like the LiDAR data or the camera data, and overall you have this mapping. So given the location, what will be the feature map look like, which is T. But if you don't know about this location, I only know about the sensor readings, only know the LiDAR scans, or I only know about the camera views. Can you compute how the X are distributed? Well, yes, right, you can. Because you can compare the point cloud and then check the similarity of the point cloud. You can use that to compute back what the X looks like, right? Okay, so when we elevate this theoretical analysis from the B, we need the ground truth location of the X and also the associated fingerprint T to finish the computation, right? This is true. This is true, but not necessarily always the case, especially when the dimension in T is much higher than dimension in X. Right? The similarity in the T, the mutant information is too high, so the conditional information, the H of X given T, this conditional information is too small, right? It's too small. If I know about the distribution of T, I know about the distribution of X as well. You don't need to tell me explicitly about the X. You just tell me how the feature map looks like. The feature map is in high dimension. I can use that information to infer back what's the structure of X. Okay? And to further support this idea, you can also check a theory called GPLVM. Right? GPLVM is a Gaussian process with a latent variable model. In that case, you don't know about x, you only know t. Right? The t is in high dimension, and you can use the t to kind of predict or approximate a hidden. That's why it's called latent, right? A hidden x, right? Only knowing the t is good enough. Right? This overall is called the GP LVM, Gaussian process with latent variable models. That's the summary. Well, then from the regression to the classification, we know regression is to map variable x to a real value t, right? And with the Gaussian, it's appropriate mapping. For the classification, I want to map from x to a class label, right? I don't want a function value, but I want a class label. Then what you can do? We can learn a function from x to the real value t. This is the regression, right? You have the complete knowledge about the model. And for classification, we want to map from the x, but to a discrete label. Can you solve this problem also by regression? It should, right? Because seems regression is a more complex problem in this case. And we can use this Gaussian process also for the classification, right? As a workaround, you can evaluate the probability of y of x between 0 to 1 being parts of this Tn, right? Because just consider this probability as a part of the function you want to learn. And secondly, you can introduce Gaussian process. This Gaussian process will give you the result in R, in the real, and you transform the outputs by additional declaration sigma, right? And finally, you get a 0 to 1 probability, right? And for classification, basically you have either 0 or 1, right? Either 0 or 1. And what can be this sigma function? This sigma function, for example, a logistic function, right? Logistic function, or the CDF or Gaussian distribution. Both function looks like this, right? So you want to convert some float value, the real value, to either 0 or 1, right? Okay. Or you can use this Bologna distribution. That's easier for it to be generalized because you can control the strength of the classification by the value t, right? The value t. So how can we do the classification, right? Firstly, the idea is similar as a regression, right? You do exactly the same thing as the regression, right? Exactly the same thing as the regression, and you get the distribution of the mean around the new predicted t. And the second one, you apply this sigma, right? You apply this sigma. Because finally, we want some binary classification that can be expressed as a marginalization over the A, right? Marginalization over the A. And that A is not even has to be Gaussian, right? So you can use some approximations, right? You can use some approximations to the A function, right? To this A function. Because it finally is just a scalar function, right? It's just a scalar function. And how to do the approximation? There's a textbook for the machine learning and pattern recognition of Bishop, right? You can go to that chapter if you want to know about more detail. But the idea is quite simple, right? We use a central limit theorem. That means infinite sum of the mixtures of a Gaussian give you what? Give you a Laplacian distribution. What is the Laplacian distribution? It's most of values is around the mean. You can, if it's a zero mean, And Laplacian distribution, it's basically seems like there's a peak, right, around 0. So a lot of zeros. As a final result, you get a lot of zeros. This is Laplacian distribution, right? How do you get Laplacian distribution? It's basically it's an infinite sum of a mixture of the Gaussian, right? So you get so many zero mean Gaussian, right? You add them infinitely, and finally you get the Laplacian distribution. So that's why you can use Laplacian to approximate, right? Approximate the functions which are constructed with the Gaussian distributions. Like center on the mod, if the mod is 0, then center on 0. And it's a logarithm shape. You can use the order 2 Taylor expansion to expand the Gaussian distribution as approximation of the Laplacian. Right. Okay. Inversely, no matter how you did that for the page 22 to 2025, the idea is to have a function A. This function A is a process to convert your previous regression results into another value. This value is easier for you to deal with the classification. Okay. If you want to know more, you just go to check the textbook of Laplacian, and I assure you this part is not in your midterm. The Laplacian approximation is not in your midterm. I just want to give you some extension of the Gaussian process. You know that it's not only limited to the lecture today, right? It's not only limited to the lecture today. And another very good resource to check is this website, right? It's the GaussianProcess.org. Okay, that's some properties of a Gaussian process, regression, and we don't consider as a main part, but you should know that we need some intermediate variable A to remap from the regression result to the classification. Okay. You have answered all the questions, so we skip the question. And I'll give you another example. In this example, we also try to use the fingerprints to learn the location, right? To learn the location. This is so-called visible light communication-based localization. If you're interested, you can go to our research website, ramlab.com. Research. We have a special research page on this problem, about this problem. So all these green dots, they are nothing. They are just what they are LED lights. They are LED light, and each of the light is flickering. Right? They are modulating. It's modulated. Right? They will be turned on and off very fast, right? In a very fast way. So it's not detectable by human eyes, but is easily detected by the sensor like flow detector or CMOS camera. So every of these will be LED lights. So at every location, you can receive some light signal from the neighboring lights, right? From neighboring lights. Then you do the decomposition of these lights, you can get what? You can get a fingerprint. You will know how much of the light signal components are from the light bulb number 1, number 2, number 3, 4, 5, 6, etc. Right? And then that serves as similar to the Wi-Fi-slam as a fingerprint. So for these locations, and also every light will give you a likelihood, right? If you assemble all this likelihood, you compile all this likelihood, this is the overall likelihood function, as wrote already there. It's the overall likelihood function, P given X. If you already know partially the motion model of the sensor, and you have the PO given X times the PO, and you have the PX given O, right? Then you get the posterior of the location. In real world, this looks like this. So on the right, that's the modulation patterns. So that means every light, the first light will modulate like this one. It will turn on, off, and off, etc. And then we have quite strong the ego correlation, or the so-called autocorrelation. And we have also quite weak, very weak cross correlation, right? So finally, the correlation map, the covariance matrix looks like this for the light signals, right? For light signals. That means if you're under one of the lights, maybe you're under this light, then you observe some pattern. If you see that pattern, then you are quite sure that you will be on under this light, right? That's the auto correlation is very high. Also, you can have little chance to mistell different lights. That means the cross correlation is quite low, right? We choose all these patterns from the golden coding, and then you have what? You have a fully running system. This system, you just mount a photodiode, right? It's a photodetector on a PC, and you collect all the lights, right? Collect all the light signals from a photodiode. It's a composition of the light signal, and then we unroll, right? By the deconvolution, we unroll each of the signal components. And if you have 10 lights in this room, 10 light tubes in this room, and then you have a 10-dimensional feature vector, right? You have a 10-dimensional feature vector. And this 10-dimensional feature vector will serve as a fingerprint location. Okay, so you can see that that's the table in the middle, and that's where students standing. Now it's moving to the corner of the table. I'm moving forward, right? So this is a very low cost indoor localization method. And also we deployed the subsystem to the HKUSD library as well for the prototyping. Okay, so that's another application of Gaussian process. But you can see that for robotic application or any data analysis related problem, if you have a high dimensional feature and you don't have fully understanding of the data space, you can use the Gaussian